Okay, good morning. Can everyone hear me okay? Terrific. Well, welcome. If this is your first day to the conference of Congress on Water Plant and Water Crisis. For those of you who were here yesterday and Monday, welcome back. We have what promises to be an exciting set of sessions this morning. We have two with a coffee break in the middle. The first one, we're going to have three speakers. Before I introduce the first speaker, if everyone can remember to please push your cell phones to vibrate so that our guests are not interrupted. My name is Trevor Birkenholtz. I'm in the Department of Geography here, and I'm going to be moderating the session. What we're going to do is have three 20-minute presentations, which then will be followed by a Q&A period. So I'll ask you to hold your questions until the end. Having said that, our first speaker today is Murugesu Sivapalan, who goes by Siva, and he's going to be talking about time-scale interactions and the coevolution of humans and water for socio-hydrology. Siva.
Thank you. Can you all hear me? I'm not sure whether something here. Hopefully this is, yeah, okay. You know, I'm a hardcore hydrologist, and here I am speaking in a session on water governance. So I decided that I'll change, even though the title is there, I'll change my talk slightly so that I can steer the talk towards the governance idea. So start with the idea, the title of this Congress, Water Crisis. So the first question is there a water crisis? So if you take a look at these pictures here, yeah, there seems to be a crisis, but it seems more like a drinking water crisis. So let's take a look, some more detail. The numbers that here are kind of rounded off for your convenience, but if we individually, we are all using about, or we need about 1 cubic meter of water per year per person. But then you look at the second set of numbers. If there's a drinking water crisis, there's even a bigger crisis because we need 10 times more water for sanitation. So the crisis that we have is not so much a drinking water crisis, it's a water for sanitation or health crisis. But then you look at the next number, it's 10 times more. We need 10 times more water for industrial uses. We heard about water for energy yesterday. So we need water, so more water, so it's more like a water for energy crisis. But then you look at the last number, we need 10 times more water, 1,000 cubic meters of water for food. And in fact, that's the number that I'm going to use from now on as to how much water we need. So it's more like a water for food crisis. So, but then we also have to put in here that we need water, but nature, environment needs water too, to carry out all the services that it provides to us. Now, if you ask the environment, or if you ask nature, how much water do you need? Of course, it cannot speak for itself. But if you give the environment ability to speak, it will say, I need all the water. In fact, that's what it will say if they have the ability to speak. But we have to speak for the environment. Forced to speak for the environment for our own selfish reasons, because good environmental health translates to good human health, as we heard yesterday. So we make this decision, we make this choice on our own for the environment, and at the moment I'm not able to give a number. How much water do we need for the environment? That's a difficult choice, but we have to deal with it. Okay, that's the demand side. Let's talk about the supply side. How much water do we have out there? This is a very complicated picture. This is a hydrologic cycle with numbers on it. And there's lots of numbers. All of them are big numbers. But first numbers I want to look at is something called the blue water. Over here, I hope. Yeah, here. 45.5. That's the amount of water that's flowing down the rivers to the oceans. That's 45.5 trillion cubic meters of water per year. a lot of water, too many zeros to deal with for us. And then the other type of blue water, which is groundwater, 23,400 trillion cubic meters of water, which is stored on the ground, half of which is fresh. And then there's a third kind of water here, which which is called the green water, and I will come back to that. That's also about 65.5 trillion cubic meters of water. I will explain that in a bit more later. But so these numbers are too hard for us to deal with. And so what I'm going to do is to sort of personalize it. So there are 7 billion people right now. So I'm going to divide the amount of water that we have, divide by the number of populations. So that brings the numbers down to manageable numbers. And so if I did that, so if I look at the freshwater flows, which is the renewable blue water, 45,500 billion meters of water per year. If you divide by 7 billion people in 2015, that works out to 6,600 cubic meters of water per year. Compare that to 1,000 that we need. So you would think that, oh, there's plenty of water. But then I think we have to also realize, we just discussed the question, how much water we leave behind for the environment. So we have to make a choice. What choice do we make? So I took the choice arbitrarily. Let's see that we take 10% of it and leave 90% to the environment so that it flows down to the ocean. That's a choice. Everybody will make a different choice. And then I do the same thing for the groundwater, blue water, 23,400, and then only 50% is fresh water. But this is not renewable. So I have to factor in that if this is renewed every 234 years. That's the average reference time. So I divide by 234 by 7 billion people, by half, which is the fresh water. So I get about 7,000 cubic meters of water per year per person. But again, I have to make a choice because I don't want to use all of it, because if I take all of it, then this is the water that actually also contributes to the river flow. So you don't want to do that. So I again made a choice. I'll take 10% of it and leave 90% of it on the ground, because otherwise I'm killing myself. So how much water are people actually extracting? How much blue water are they using? Withdrawals, these are the numbers for the different countries here. Of the US, we are using double the 1,000. And then going down to Nigeria, which is only using 50. So how can Nigerians live with 50 millimeters of water per year when they need 1,000? So the explanation comes from green water. So in other words, they can produce the food not with the fresh water flowing down the river or in groundwater. They actually use the green water, because you have rainfall going to the ground. Before it actually gets to groundwater or running off, there's a certain amount of water in the soil, in the unsaturated form, which we humans cannot drink. You try putting a straw into the soil and try to suck it, you can't do it. We cannot do it, but plants can't do it. So plants are using this and they produce food for us. So there's value in this green water for food, and food is a majority component of our water needs. So we can cover that, and so we have quite a bit of water there, but 65.5 trillion. But then the land cover there's forest, 41%. And for our own sake, you don't want to tap into the forest. You don't want to cut down the forest. So we want to leave the forest behind. So we only want to use the rest of it, which is about 26. So how much green water do we have? 65 trillion. And then I avoided the forest. And then it comes down to about 26,000. And then, again, for my own self-interest, I said, let's not only use 20%, because the efficiency of agriculture is not so great. So that's another choice. So it again came down to about a number 740. You would think that I'm playing fast and loose with numbers, but you know that these are choices that we make, and these are difficult choices. And I just do this just to make sure that the total number of fresh water that we have, 700, about 2,000. So so look at the equation, 1,000, 2,000. 1,000 is the demand, 2,000 is the reliable supply that we have. That's what we have to manage. But then we have to also worry about changing lifestyles. This is an example of China. So China was using only about 300 per person, 1961. Now they're using already 800 in 2003. They're going to go up. So lifestyles are changing, India, China, And so the 1,000 is not going to be sacrosanct anymore. It might be going up to 1,500 for that matter. And then the population is increasing from 7 to 9 to 2050. That means that the equation 2100 that I decided before is going to come down to 1,600. So the balance is we have almost equal. What we have is what we need. That's okay. In other words, if you want to have a healthy environment. But of course, this is all global. And the reality is that people are distributed non-uniformly across the world. And so we have to divide the available water everywhere, divide by the number of people there. And then you get a really non-uniform distribution. This is the amount of water, fresh water flow available per person per year everywhere. And you can see that enormous variations. And if you choose the number 1,000 as the baseline, then you get lots of places that have less than 1,000, lots of places that have more than 1,000. But then I haven't even factored in the fact that I can only use 10% of it. Okay, so this is a problem, distributional problem. And of course, then I have to add this is not uniform. You have high years and low years in precipitation, so there's temporal variability in this. And then you have to introduce climate change. Climate change doesn't affect the total amount of water that we have, but places that have plenty of rainfall now, they may change, they may go down. Places that have less rainfall may go up, so there's an uncertainty created by climate change. So coming down to it, if there's a global water crisis, it's not the crisis because we don't have enough water, but it's a management crisis. Okay? So we have crisis in water management in the context of fast increase in demand, including the fact that we have to provide water for the environment, decline of a poorly distributed source, because if you pollute the source, you are declining the fresh water. Total amount of fresh water is not changing unless you pollute it, in the presence of considerable uncertainty, climate change, for example. So it's an optimization problem. And we engineers, hydrologists, I don't think it's rocket science. You can do it, okay? But is it rocket science? So I emphasize along the way that we have to make choices. There's a lot of choices that we have to make. So we have to make choices between water for human consumption, for sanitation, for food, for energy. So which one is more important to us? Water for the environment. Do we care for the environment more than we care for ourselves? So there is a competition for water between different human beings, because different people need different things, expect different things. So water, food, energy nexus basically is an example of a competition between different communities. Rich and poor, they have different expectations, different preferences, upstream and downstream, between humans and the environment. And trade-offs between short-term needs and long-term consequences. That's another decision that we have to make. So if you think this is still an optimization problem, what is the objective function that we're going to use? Do we know what we want? Because different people think that they want different things from water. So we like to think that we are rational people. Nature follows natural laws that we understand, we try to understand. Nature tries to optimize things, to self-organize. So we benefit from these natural laws and natural optimality principles that nature tries to follow. But when it comes to humans, so I'm thinking like the system that we are studying is the combined coupled human-nature system. Nature has its laws, nature has principles. When it comes to humans, we like to think that we are rational, but you look at the number of BMWs on the roads in Champaign driven by undergraduates, that doesn't mean that we are rational people. So rationality goes only so far, but that doesn't seem to be applied in real life. And then we don't follow our own laws. We create laws. We have speeding laws, but then we speed and are prepared to pay the fine. So these are human aspects that we have to bring into the table if you are going to properly manage it. So it's additional complications that we are dealing with coupled human nature systems. So instead of rationality, instead of optimality and so on, this is a fantastic paper that appeared in PNAS just a few weeks ago by Caldas et al. Look at this thing here, important to understand and model the influence of cultural factors and associated values and preferences, which are likely to be more predictive of human behavior than assumptions about rationality and utility maximization. So in other words, they're arguing that culture and values and preferences should not be externally imposed, but they are self-organized. They are internally generated, endogenous to the system. That's the way that we have to treat the world. So I want to talk a little bit more about human preferences and values, and this is a definition from Jim Westcott, who used to be here. Values are overarching goals of individuals and whole societies with respect to water use, conservation, and sustainability. And preferences are formed by humans by selection acting on traits that are transmitted both genetically and culturally in a co-evolutionary way. This is the point I'm trying to make. These are internal, endogenous, and therefore values are not fixed. Values change. Values change in time, values change in space, under the influence of education, advertising, changing cultural assumptions, and the dynamics of the water resource system itself. In other words, we deal with the water day by day, and we learn and we adapt. That is also part of it. So we have to deal with dynamics of changes in values in managing water. So this is a picture that we came up with recently, how to model values. So in one of my recent papers, we came up with a notion of community sensitivity, which looks at the question of how people interact with nature. So we have on the right-hand side a socio-economic loop where you go out and grab a piece of land and water, produce some wealth, and on the process of as you produce wealth and use the wealth to invest back in the exploitation of land and water, and you go out and grab more land, and it goes round and round, and so this positive feedback keeps on going. But then along the way, you run out of water or the resource, and then the environment kicks in and then creates a negative loop that is left on the left-hand side. And we try to model this community sensitivity as people relate to this over 100 years. Values change. So early in Australia, in this first 50 years of the time, the focus was on economic factors. So they were not prepared. They were not care about environment. They just went out and extracted land and water, produced wealth. That was the focus. But then the environment kicked in, environment degraded, and then it turned around, and we call it the pendulum swing. So this is an example actually observed in Australia. And then we can also have values change in time. But if you have a system like in Florida, in Kissimmee River Basin, you have the upstream and the downstream. And upstream people have one set of values because they are urban. The downstream people have another set of values because they are rural. And they compete. And the people who are stronger, economically, politically, they win out. So there's competition between different groups of people, value their values, and that plays out in the landscape. And that explains why in Kissimmee, 50 years ago, they had floods. They straightened the rivers. 50 years later, they go back and they put back the meanders again. So they invested $100 million 50 years ago. They go back and invested $200 million to put back the river. This is what we are having everywhere. So these are because of value change with time. So these are manifested. Yeah, okay. So I don't want to go through. So I'm seeing this kind of change of values all over the place, and I'm actually involved in 4 different collaborations in Australia and China and Florida. And this is playing out everywhere, this kind of thing, and contributing to what we call unintended consequences. Now, and the tyranny of small decisions. You heard a classic example of the tyranny of small decisions yesterday in Jay Familietti's talk, that there's this long-term thing happening, and people are blaming the whole thing on the drought. Okay? So something that is happening, there's a cancer growing, and you blame it on some, that you don't have enough exercise in the day. So this is the kind of thing that can happen when you actually don't bring in the human element into this. Another example is in China, where we actually experienced that, okay, the people actually learned, we can't degrade the environment, so they actually set in measures to improve water use technology, and they were very successful at it. They're so successful, the farmers had extra water in their hands, and instead of leaving the water in the environment, there was nothing stopping them. They went out and grabbed more land. And so while efficiency went up, consumption went up, as this figure shows here. So that's an example of poor governance. So one set of people think one thing, they decide certain actions. Another set of people say, we have other things. So, and there's no alignment between the two groups of people. This is the classic example of poor governance. So if I come back to this, if this is a crisis, if there's a water crisis, instead of calling it a crisis of water management, I would call it a crisis of water governance. So water management in the context of, you can read all about it, but it's really bringing all these new factors, especially changing values over a long period of time, the underlying cancer that is growing. So it becomes a dynamic optimization problem where we have to involve internally the changing values. When you do that, when you bring that aspect into the system and you bring in social sciences, it does become a rocket science after all. So it becomes a very difficult problem. And this is exactly what led to our introduction of a new field called socio-hydrology, where we have to involve the humans and the nature together as as interacting system with two-way feedback that are internalized. And this is the way that we can actually address this governance problem. And if you want to know more about this, we have two papers that are recently published in Water Resources Research, one on timescale interactions, which was the title of my talk, and another one on the tyranny of small decisions. I'm not going to talk about the timescale interactions, but I'll just leave these figures on there to explain to you that we are dealing with two different systems, fast and the slow, interacting together, creating new dynamics. And these dynamics can lead to all kinds of complex trajectories that bottom figure explains. So you can have an economist dream, everything is perfect, and then another trajectory is the environmentalist nightmare, where you actually, the system crashes down, or another way, it crashes, but then we find a way to fix it and come back to recovery. So I will just stop there. Thank you very much.
Terrific, thank you, Siva. I think that we could also think about launching a science of unintended consequences, which would cover a lot of what we're talking about. Let's see here, I think Jody says right here. Is that right? Terrific. Great, so our next speaker is Jody Endres, Assistant Professor of Law in Natural Resources and Environmental Sciences at the U of I. She's going to be talking about designing governance systems to solve nutrient pollution, lessons from the Clean Water Act litigation.
All right. Thank you, Trevor. Shifting gears a bit to a hardcore lawyer instead of hardcore hydrologist like Siva, and I want to say thank you to Evan and Madhu. We've worked before in the past in these multidisciplinary sort of efforts. Thank you for inviting me here to speak about, as Trevor said, how we design governance systems. We're going to see, even though I'm an attorney and we have hydrologists and economists here, there's really exciting ways that I think my presentation can tie into what the panel is talking about. So I've tried to attend as many of the sessions here as possible. I have a heavy teaching load, but I really do see, and congratulations to the organizers, this centralized theme emerging from the conference. And whether it's Professor Kumar, who I am excited to look again at his slides about designing these systems level frameworks to solve what we call complex or novel, global, massive water problems in quantity and quality, or the multidimensional nature of disciplines needed spanning the physical and social sciences, which many of our speakers highlighted for us this week. And I really enjoyed the remarks by Professor Knapp yesterday about science focusing on problem solving, the need to focus on longer range experiments, and finally, and this is what I'm going to focus on today, is Professor Shortall's, he alluded to it very nicely about this debate regarding what institutions should be responsible for pushing or leading or solving, or in the legal profession we might call nudging in theory. So that's what I'm going to focus on specifically, and this is what my research generally focuses on in academia, the role of regulative institutions in this pushing and nudging and solving to get at the core of why we're here, water problems. So I'm going to specifically be confining my remarks to federal agencies, Congress, and courts, and you'll see how I do that in a minute. But I first want to start off with introducing you a bit to what I find one of the core theoretical bases in our profession, And I would recommend, it's a long article and it's written in a law review article, but I actually do teach this to my students in a boiled down version. This article, Climate Change, Dead Zones, and Massive Problems in the Administrative State, a Guide for Whittling Away, by two very prestigious professors in environmental law, J.B. Rule at Vanderbilt and James Salzman at Duke University, published in the Cal Law Review in 2010. I was really struck by their analysis of what I teach to my students is really the core environmental opinion, at least of this century, and that's Massachusetts versus EPA. That's the decision that led to all the regulation at the federal level now that we see in greenhouse gases. An example, complete example of a massive problem, and Justice Stevens authored that opinion. And in that opinion, one of my favorite phrases is, in the context of climate change, an agency should whittle away at massive problems. So Professors Rule and Salzman, in their article, which actually was voted for that year by the ABA, the most impactful environmental law published in the United States, if not internationally, they posit that we can borrow from different governance theories in this journey that we got in answering how agencies can be empowered to, as Justice Stevens would say, whittle away at these massive problems. So they focused on, or gathered, three not so differing, they're quite overlapping approaches to governance, whether it's dynamic federalism, which, and I'm quoting from them, we believe that settling on the sole approach of centralized federal power, that's important, we'll see in a minute to me, versus devolved state power, dual federalism, we hear cooperative federalism a lot. Salzman and Rule find that unproductive. And instead, they highlight for us the concept of overlapping federal and state and through states' local jurisdictions and multiple levels of government interacting in the regulatory process. So that's dynamic federalism. They look at new governance theory, and I think Siva really did allude to this in the latter part of his presentation, the importance of these stakeholder groups participating, collaborating, bringing in diverse interest, a decentralized governance structure, integration of policy domains, flexibility, and an emphasis on non-coerciveness and adaptation. Lastly, they highlight the concept of transgovernmental networks. This is a theory that sort of proliferates, I think, in the international context, but holds true also in the national context in the United States, that emphasizes, again, and this is similar to the others, this non-hierarchical, horizontal and vertical networks that are built among officials of national and international institutions. In this case, we could analogize to national, state, and local in the United States, to exchange information, identify best practices, harmonize approaches, and enforce the overall international policy program. Now, Rule and Salzman would say that you can put these types of arrangements in planning agreements, but it's more important to have those built on personal relationships. And I emphasize that to my students in law. Don't underestimate the importance of networking and communication in getting your point across. What I'm doing in my scholarship is perhaps taking a little bit of issue, both maybe with Justice Stevens, although I probably shouldn't do that, and Professors Rule and Salzman, even though I hold them in very high esteem and they're mentors to me, that my theory is that the federal government, and I think this is probably almost opposite of what Siva was saying, can do more than just nudge, and that it should lead. And this is my very probably poor attempt to put my thoughts down graphically, but I'm going to use this when I look at some examples in case law and Clean Water Act nutrient pollution litigation on how we can see, for example, agency action, of course, at the federal level, in this case, US EPA. Whether we see in these case studies in Chesapeake and the Mississippi watershed agenda setting, coordination, funding efforts, and most importantly, at least in the litigation, how EPA interprets Clean Water Act provisions. I'm at the initial sort of stages in my building of theory here that EPA, through this, can build power when we reach those situations like Siva alluded to, where we have, well, the environment kicking in and we don't have enough water. We don't have enough clean water. We already see that in litigation in Iowa. I would counter that, or maybe follow on to that, saying, well, then leadership needs to kick in, because when we're at a crossroads in policy, at least it's my theory, that some mechanism needs to be levered, and that requires some sort of power. And French and Raven, way back in 1960, sociologists sort of posited that you can exercise 5 different types of power. Legitimate power, that means that just by holding the position that you hold, meaning EPA is at the federal level, that you can exercise power in decision making. Reward power, I analogize that to funding different types of programs, and we definitely see that in the non-point water pollution context. Expert power, and we often hear of agencies and litigation being deferred to their knowledge. Referent power, and that comes the fact that in the structure, there's a building up of leadership and respect. We may see that lacking in some areas of the country, as I'll highlight in some of the litigation. And lastly, coercive power, and I think many people, when I put that statement out that perhaps we should have more federal government leadership, as demonstrated in our litigation, might say that would be quite coercive, and yes, that is an example of coercive power. But the results that you get out of that in the middle of this chart is, and I think we've focused on that a lot in this conference and a lot of these conferences where we try to think about how to solve these massive problems, we get information generation, we get dissemination of information, it's action inducing, and we get that alignment among all of these different actors. And EPA, or as the agency that I'm using in my example, does that for a whole set of stakeholders, policymakers, voters. In the non-point source pollution, nutrient pollution context, there are a lot of actors, and I really work on the ground with all of those folks, and I see that there is some need here for some agency action, and if I have time, I'll talk about that work a little bit. But first, I really want to sort of do some heavy lifting. I know it's early here in the morning, but this litigation is very recent, really interesting sort of ways of the court system, because again, we're focusing both on agencies, but also with the help from courts and Congress here on how we can, at the very least, whittle away, and I would say do better than whittle away at these types of problems. So let's test what I call my lead versus nudge theory. It's not nearly as clever as the tyranny of small decisions. I need to get much more creative. But I'm testing this sort of leadership theory or organizational theory as imposed on this problem in the law. So first I want to walk you through a decision that came out from the Third Circuit, that's in the northeastern part of the country, envelops all of the states involved in the Chesapeake Bay, American Farm Bureau Federation versus EPA, I'll just call it AFBF. It raises those questions of agency leadership, statutory support, which means Congress writes statutes, so they have to provide that leadership, and favorable court interpretation, which we got, we, in this case, supporters of in solving the Chesapeake Bay problems. So the facts of this case were, and it typically starts out this way in a story, that US EPA, pursuant to consent decrees, because the Clean Water Act contains citizen suit provisions that enable citizens to force nudge action, US EPA promulgated for the Chesapeake Bay a Baywide TMDL to address nutrient pollution. That is a classic, massive system-type problem. I think we can all agree on that. To ensure that total maximum daily loading standard was met that they set, and it's a numeric number, EPA then, by sector, agriculture being one of those, that's why we have the Farm Bureau as the lead litigant in this case, set allocations per state, not per person, set deadlines, and required what we call reasonable assurances, or in other words, exercised its backstop authority with regard to submission by states of water implementation plans, and EPA approved those. If they don't like those, they can always nudge, push, coerce. One could argue in terms of saying, well, if you're not going to deal with your point source discharges, we have clear authority under the Clean Water Act to lower point source dischargers, but there's only so much they can lower in that area. Okay, so that's the facts of the case. The issue was a very narrow one at the circuit level, and Farm Bureau argued that the meaning of total, and I emphasize total here, maximum load is unambiguous, meaning that, and we say that under a Chevron test, that's a case back in the 1980s, I believe, that gives us a test for when an agency interprets a statute. So on prong one, we ask, is the statute unambiguous? If so, that's the end of the analysis. But if it is ambiguous, then we go to Chevron prong two, and we look at whether the agency's interpretation of the statute is reasonable. So Farm Bureau argued, total means just that. You set a number, nothing else. Well, EPA didn't do that because they set sector allocations, those deadlines, and also the reasonable assurances. US EPA and amici, which included Delaware, Maryland, and Virginia, did not include Pennsylvania and New York. They counter-argued that the statute is a classic example of an ambiguous statute and therefore deference under Chevron prong two. So the Third Circuit, and I'll mention who the judges were in a minute, first looked at the text of the statute on the question of whether that total in TMDL is ambiguous or not, and they said it's not defined in statute. The statute is silent on how to implement a TMDL at the US EPA level, and that the APA, the Administrative Procedures Act, Congress had to have been aware that that law requires, if EPA would just set a number, it would be arbitrary and capricious for them not to explain how they arrived at that, which means they needed to do some interpretation and figure out how it would work. Then they went from a textual analysis, because you always start with the textual analysis, to the structure and purpose of the Clean Water Act. And they easily found that Congress, when you look at the whole act, intended US EPA to gap fill to meet those overall goals of the statute, and it would certainly frustrate the purpose of setting a total number for the Bay, not to have these enforcement type mechanisms. And then very interestingly, the court, and there were two appointees to the court that were of the more conservative persuasion, they were still in the majority, who delved into the federalism question. Because when American Farm Bureau makes the allegation that all of these EPA actions, whether deadlines, reasonable assurances, or allotments, impinge on state police powers over zoning and land use, that's going to trigger a federalism analysis. So we can divide that into, well, federalism and constitutional avoidance, two tenets of judicial interpretation. And the court found that, well, EPA's actions don't impinge on states' rights because they don't prescribe means. The states are still responsible for watershed implementation plans. It's only an informational tool, which goes at that middle part of my chart in generating information. And the court noted that, well, counsel, you're not making a 10th Amendment coerciveness argument here, and they couldn't have. I'm sure they wanted to, but the states that they would allege were being coerced were in the amici briefs for US EPA, or at least silent. So that would have been a very hard argument. On the tenet of constitutional avoidance, this has come up quite a bit in the wetlands context, in the Swank decision and the Rapanos decision, in terms of how far can Congress, under the Commerce Clause of the Constitution, push constitutional boundaries to seek to regulate, in the wetlands context, again, a water quality issue. The court said, unlike with wetlands, and Swank isolated wetlands, and Rapanos non-adjacent wetlands adjacent to a non-tributary water of the United States, there's no doubt here that Congress has given EPA, under their Commerce Clause power, the regulatory authority over an estuary. That's the classic Commerce Clause problem, and they name off the interest, fishing, navigation. It's a no-brainer. Okay, then on prong two, because they find the statute ambiguous, then once the agency gets through that, I think I teach my students a little bit easier sailing. Was EPA's choice looks like enforcement, a reasonable one. There is a particular section in the Clean Water Act, 1267, that does, with regard specifically to the Chesapeake, that's unique to estuaries in the United States, to make sure that goals are met. This is how they do that. Now here's where the language gets really interesting, so I'm just going to quote it. Although Farm Bureau claims that the bay will be cleaned up without EPA intervention, the contention defies common sense and experience. And identifying institutions, this is from the opinion, that govern large events, read massive problems, best should be an exercise in experience, not couched Chevron-type analysis. The EPA's approach, in the end, simply just makes sense. And I think oftentimes we sit here and scratch our heads. This just doesn't make sense. I think Mark David really expressed his frustration with the Gulf Hypoxia Task Force, that it's just not making progress. It doesn't make sense. So at the end of the opinion, there's some really good language carrying forward. Congress made a judgment in the Clean Water Act that the states and the EPA could, working together, best allocate the benefits and burdens of lowering pollution. The Chesapeake Bay TMDL will require sacrifice by many, but it will be the consequence of a tremendous effort, and it will take to restore to the bay to make it once again a part of the land of the living. And they quote Robert Frost, a goal our elected representatives have repeatedly endorsed, and Farm Bureau's arguments to the contrary are unpersuasive. So this is a foundational opinion, in my opinion, in the United States, that then leads us to test my theory of leadership and nudging in this chart. So we can look at here how in Chesapeake, we had an EPA pursuing an interpretation of the Clean Water Act that led us to a court decision that is favorable for cleaning up the estuary. So it's key that we have, coupled with that EPA leadership, and I don't have time to get into all the other beneficial aspects of their approach, but we do have a statute that was written with deference to the agency, because agencies can change, of course, but teeth. And the court really ascribed in this case to a traditional notion of broader federal power under the Commerce Clause. And I have here now that there was a Clinton appointee, a Reagan appointee, and a George H.W. Bush appointee, all in the majority in this case. That to me speaks to, contrary to what we see in the Supreme Court with our newer appointees, a sort of recognition of massive problems and at the core why we have the Commerce Clause in cases such as this. Okay, 3 minutes, all right. I want to quickly touch on a case that is now ongoing. Really exciting litigation. I'll dig into it for you, hopefully summarize it well. Gulf Restoration Network versus US EPA. This is a Fifth Circuit opinion because that is within the jurisdiction of the Mississippi watershed where it lies in the southern United States, Texas, Louisiana, Alabama. So let's ask the same question. Are we seeing agency leadership? Do we see statutory support and favorable court interpretations? Well, the facts of this case are a bit different. Environmental groups have asked US EPA to set water quality standards under Section 303C. 303C, here's the language, because remember we look at from the Third Circuit the actual language of the statute, total. Here we have language that says the administrator shall promptly prepare water quality standards if a state submits a standard that's not consistent with the statute, or EPA determines that a revised or new standard is necessary, and environmental groups are pleading it's necessary. Gulf hypoxia is a problem. So EPA refused. They said, we're not going to make that necessity determination. We'd rather work with states. The environmental groups went to the district court. The district court said, yes, EPA has to make that necessity determination, but we're not going to delineate what factors you rely on. Perhaps you can rely on political factors here. Oops. And this is where Massachusetts versus EPA, even though a Clean Air Act case becomes very precedential, very exciting, because it went up to the Fifth Circuit. They reversed, relying heavily on Massachusetts versus EPA, saying that EPA can refuse to do the necessity determination, just like under the Clean Air Act context, but you have to explain why as an agency within the bounds of the statute. And that's where, so if we test this theory, we'll see, and I don't have much time here, but I want to analogize to the American Farm Bureau case. On the Chevron prong one, if we do a Massachusetts versus EPA type analysis, I don't think the statute looks too ambiguous. And that was the language that I quoted to you. Structure and purpose. The statute as a whole contemplates EPA enforcement. We draw that from the Third Circuit opinion. On the federalism question, water quality standards wouldn't prescribe means, just like TMDLs and watershed implementation plans, and we're already getting cooperative in the watershed. States would object, I think, unlike in the Farm Bureau case, but on the other hand, those states would be given a little bit of political cover if US EPA would do that determination. And lastly, there's no question again that the Commerce Clause clearly encompasses the Gulf estuary, just like it does in the Chesapeake. There's no difference there. And this is my last slide on the Chevron prong 2 analysis. When we're doing this Massachusetts EPA type analysis, then we look at the purpose of the statute, not politics. That was the issue in Massachusetts versus EPA to determine whether refusal to conduct a necessity analysis is a reasonable policy choice. I would argue it might not be. This is going to be a hard case for US EPA to litigate because it's back now in the district court. In the Farm Bureau case, the focus was on experience, not logic. We have the same experience here with Gulf hypoxia. Does EPA's differing approach in the Gulf restoration case make sense under the statute? Clean Water Act has been interpreted as a hallmark of cooperative federalism, yes, but the Farm Bureau case in the Third Circuit emphasizes EPA's roles if states are not successful. And should it matter that a pro-plaintiff decision could reasonably lead to political uproar, because that's what I always hear in the Midwest, leading Congress to change the statute, which would be terrible, but I would counteract that Congress is so ossified that's not going to happen anyway. So EPA could exercise that leadership. They did it in Florida. I don't have time to cover that. That's the third type of circuit case going on right now. But with that, I'll just say thank you, food for thought, and hopefully we can parse it out in the discussion. Thank you for letting me go a bit over.
Great, thank you, Jody. That was fascinating. Let's see here. I have chug, chug, chug. Let's see, do we need to close that one first? Shouldn't, but. Okay, there it comes. Okay. Terrific. So we have our third and final speaker for this session and organizer of this event, Madhu, Khanna, Distinguished Professor of Environmental Economics here at the university. She's going to be talking about understanding the nexus between food, energy, and water quality, challenges and policy implications.
Thanks Thank you. So I thought I would pick up a little bit on the themes that were raised in session 2 yesterday, particularly Mark, David, and Jim Shortle talked about water quality management and issues, and try to raise, sort of highlight some of the complexities associated with this, understanding this interconnection between food, energy, and water. And then based on some of the work that I've been doing, talk about some of the emerging, potential solutions, the technological solutions that are out there that could impinge on this, and what that implies for policy in order to try to get there. So just to start off, we've made impressive improvements in agricultural production. In the last 50 years, we have tripled total agricultural production. There's been a 6-fold increase in the amount of biofuels that we've produced in the last 2 decades. And although it's sort of from small amounts, but still it's a pretty impressive increase that we have observed. And these are really crop-based biofuels, so it's adding to the amount of increase in meeting the demands for food and fiber and so on. And all of this has really been achieved through intensification of production. So increased amounts of fertilizer and other chemicals has contributed significantly to this increase in productivity, all of which has contributed to an increase in the footprint of agriculture on the environment. And it's impacting a variety of, the environment in a variety of different ways. Of course, land is the biggest factor that is being used both intensively. There's been, of course, an extensification of land. Freshwater use for irrigation. That irrigation is, we've learned, over the last day and a half, a major, source of demand for water. It's also led to water quality contamination. And in addition to that, agriculture is also a big source of greenhouse gas emissions, even after we factor in the sinks of carbon in the form of forests. Okay, so one of the key issues if we focus particularly on water quality issues, one of the key factors contributing to that is the amount of nitrogen that we're using. And not only is that we're using a lot of nitrogen, but half of the nitrogen that is actually applied runs off. And you could increase productivity or maintain productivity by reducing or using much less nitrogen. And of course, this problem is localized. So it's not that nitrogen applications everywhere are equally damaging, but these are in particular areas that are more susceptible to runoff and leaching and so on, that this is a particular problem. And this is a map from a science article showing areas of hotspots where, in fact, nitrogen causes particularly large problems. In the U.S., it's in this Mississippi River Basin, Midwest and below. Okay. We've talked a little bit about unintended consequences today, and one of the factors, if you overlay where the nitrogen problem is with, how policy contributes to it, these are also the areas where we have large federal, commodity support programs, subsidies going to farmers in various forms, crop insurance, which is also heavily federally subsidized. You can see where the crop insurance payments are going, and so policy can have this unintended consequence of actually, affecting this nexus between food and water quality and contributing to some of these water quality problems. We talked a little bit about this yesterday, that this is, it has an impact on these dead zones that are being created. There are about 400 of these hypoxic zones where there is an excess of nutrient, and it makes it very inhospitable for aquatic life to survive. In the U.S. in particular, the Mississippi River Basin, the Gulf, the Chesapeake Bay are some of the areas where you have this problem. All right, so one of the points that I want to sort of make is that when we're thinking about the environmental impacts of agriculture, water quality is not an isolated impact. And really the impact of agriculture is multidimensional, it is complex, and so trying to understand and manage that becomes quite a challenge. And so just looking at two of these impacts, one of which is water quality, the other is carbon emissions, and the two are interrelated. Tillage, we rely heavily on conventional tillage in production here, leads not only to runoff, which contributes to the water quality problem, but also leads to a loss of carbon stored in the soils. And so you can see from this graph on the right, we've lost about 50% of the carbon that was stored in soils since in the last century or so, just because of the tillage practices that we have been using. Similarly, fertilizer, on the one hand, of course, increases productivity, but it's the third largest source of greenhouse gas emissions from agriculture, and it also is a major source of greenhouse gas emissions just because of the way it is being produced. The other aspect of it is that the same type of product can have conflicting impacts on the environment. So if we think about corn ethanol as an example, this is it was, of course, one of the motivations for that was to reduce greenhouse gas emissions from our transportation sector. But because it's so heavily reliant on corn and therefore on fertilizer, it has a negative impact on water quality, while it may have some positive impacts on greenhouse gas emissions. And so you'd think that, well, ethanol has this conflicting impacts. On the other hand, if we think of other types of biofuels, and so cellulosic ethanol that we'll talk about just in a minute, that relies upon energy crops might in fact be synergistic, because not only can it reduce greenhouse gas emissions, it's very low carbon intensity, but it can also reduce nutrient runoff and therefore improve water quality. So that requires really nuanced thinking about this nexus between food, energy, and water, and where are the complementarities and where are the the conflicts. Okay, so trying to capture some of that through this graphic, we've got these demands for food and fuel, of course, that work their way through the market and impact land use, and through land use they impact a variety of different dimensions of the environment. And this nexus is affected by government policy in a variety of different ways. The government policy creates demand for biofuels. Government policy affects the market-based incentives for food production through the types of subsidies and other support programs that they have. They affect the type of management practices that are used in agriculture. We learned yesterday about the various ways that there are a number of different financial payment programs through which the government subsidizes best management practice adoption. And that affects land use. And so this is, it's a pretty complex way that government policy or governance in particular affects land use and technology choices. And then the impact of these on the environment is highly uncertain, because it is there's intervention by the weather. And so the same type of practices may not be as damaging under certain weather conditions, may be very damaging under, if you had a big rainfall event, then a lot of runoff, it could have a very negative impact. So all of this creates a lot of uncertainty about the impact of crop production on the environment, which makes governance that much more difficult. A second factor that makes it very difficult is that there is a lot of spatial variability in this impact. So it's not the same everywhere. Praveen mentioned yesterday about this being place-based, and that is completely true. This is a very site-specific problem, and therefore it needs, to be effective, needs site-specific solutions rather than a one-size-fits-all type of approach. A third issue with governance is the fact that the type of pollution that is being generated by agriculture is of a non-point nature. So it's very difficult to link the pollution to the source and to hold the source accountable, unlike in the case of point source pollution, where you know exactly what's being generated, where, and how much. And then a third aspect is that it is multidimensional. So you might try to control water quality, but that could have a negative impact on greenhouse gas emissions or vice versa. And so you have to manage the system as a whole if you really want to improve benefits across the board, rather than trying to solve one problem by creating another problem. And so an example of that is, we have policies for biofuels, which are designed to improve our energy security, to mitigate climate change, but these can have a negative impact on water quality if you focus on the wrong type of biofuels. So what I want to talk sort of next is just some examples from my work and work that's sort of emerging in looking at some potential technological alternatives and what kind of policies are needed in order to move in that direction. Okay. So one of the things that there's been some work on in the past, and I think it's gaining much more importance now, is this idea of prescriptive farming. So the issue with fertilizer is really this Goldilocks problem of getting it just right, and it's very difficult to know just how much fertilizer should a farmer really apply, what is exactly needed by the crops. Sort of matching the needs of the crop to the application. And that's just a very hard problem for a variety of reasons. In order, even from a sort of an agronomic perspective, fertilizer moves a lot. It's very dynamic. Figuring out, agronomically what the right application rate is challenging. And then you have to, once you've figured out what should be applied, then you need technology that can vary the rate at which you're applying the fertilizer within a field that may be very heterogeneous. And so, precision agriculture, it's been, I think, about 25, 30 years. It's been emerging. It's been slow to get it to be adopted, but that's sort of one approach that you could reduce your nitrogen use without necessarily, or even increase your output while reducing your nitrogen. Another example is efficient irrigation technologies, and we have a variety of ways, sprinkler irrigation, drip irrigation, that can increase the amount of effectiveness by which water is actually taken up by plants, reduce the runoff. And we heard in one of the talks that how flood irrigation is still very widely used, and flood irrigation is the most inefficient way to apply water and waste water, as well as causes runoff problems without benefiting the plant. So, using drip irrigation, scheduling the irrigation based on the needs of the needs of that particular field and the crops would be another approach. So all of these are approaches that you can increase the efficiency with which inputs are used, increase yields potentially, while reducing your input costs, decreasing runoff, and also reducing the risks of farming by being able to improve your management. And so a number of these data-driven solutions for irrigation, for site-specific management of fertilizer application are in fact emerging. And they've been there now for a couple of decades. But when you think about farmers, they're going to be making a trade-off, or they're going to be looking at, well, what is the cost of adopting these types of technologies, and what is the additional benefit that you're going to get from that? And so a lot of we've done some work looking at surveying farmers, trying to do this analysis of really who benefits from it, or under what conditions would farmers benefit from it. And a number of things that have emerged to explain why adoption rates have been very low. High capital cost is one of the reasons, long payback periods. The returns are very uncertain, and inputs are pretty cheap, so fertilizer is relatively low cost. Outputs have been, corn prices and so on, except in recent years, have typically been fairly low, and so it hasn't justified the kind of expense that's needed to be able to manage this, fertilizer variability. And of course, there's been very little mandatory requirement to do that. So all of this has been very voluntary, and it happens only if farmers think it's going to be, it's going to benefit their bottom line. And so this graph on the bottom shows that of the people who adopt the yield monitors which monitor the yield as you go through the field, harvesting, the adoption rates have been about 30 to 40% in the last 2 decades. And of those people who adopt the yield monitors, less than half, and even in some cases, only about 20% or so actually adopt these variable rate technologies, or the GPS technology that tells you how that variability is allocated across the space of your field, and how to manage it, and to actually vary your input application rate. So actually the actions or the decisions that can lead to changes in application rates, the adoption rates have been really low. And one of the reasons for that has been the fact that although you can gather all this data from the technology, converting that into decision rules there's been a big gap in that. So you may know what the variability is in the field, but it can take, but you really don't give the tools to the farmers to be able to know how they should respond to it. And so interpreting the data and deriving these decision rules has been one of the key challenges to this in the last decade or so. And in fact, that's the reason why the technology sort of plateaued. But of course, this is changing now. So we've now moved into this era of big data, and big data is got these major big companies, Monsanto, DuPont, John Deere, Pioneer, that have made very large investments in being able to gather the data from the fields of the farmers and convert that into decision rules that they can use in order to vary their nitrogen application rates, their, vary the seed planting rates, pesticide application, and so on. And so these are a number of commercial products that have now emerged where farmers can sign up, and they are giving access to their fields, and they're using the technology provided by these companies in order, as they're doing their crop management and planting, and then all this data is being generated and being used by these programs to convert that into real-time decisions about seed, planting rates, pesticides, fertilizer applications. But the idea is you're combining multiple sources of data on soil characteristics, weather, crop management practices, and so on, using very sophisticated technology in order to enable better decision making and to vary those your decisions as you're going through the field, applying various inputs. So the future of this could look like where all of this data goes into a data bank, and then you've got a number of different input providers and others making using it to make their decisions. And so the question is that how do we have more, how do we induce more adoption of these types of, get more farmers to practice this? And then how can we use this to improve the way that we can, regulate pollution or create further incentives so that all of this results in some improvement, societal benefits in terms of improved or reduced negative environmental impacts. And so, like I mentioned, agricultural pollution is difficult to, observe, measure, and monitor. And that makes it very difficult to really to identify effective ways to, we talked about you could have carrots and sticks as your policies. Carrots could be these uniform or, subsidies and other payments in order to adopt. It's very, increasingly very expensive for the government to be funding and inducing these types of, adoption of these types of practices. And so if you're thinking about sticks, then as a way to control pollution or create incentives to control it, then how do we design policies that are in fact recognizing that the environmental damages are site-specific, that these policy incentives need to be targeted to specific locations and certain types of practices, so that we can move away from these practices that are just compensating farmers for very in a very sort of crude way of retiring land from crop production, which is so expensive because you have to compensate farmers for lost production, adopting these best management practices. And instead, can we use big data that we're generating, which is really can be converted into, could be used to convert this non-point pollution problem into a point source pollution, because exactly what was the site-specific characteristics of the field, what particular practices were being adopted there, and so you can use that along with technology to figure out exactly how much pollution was generated from which part of the field and from where did it originate. And that could enable effective spatially differentiated policies that could be much more targeted, would be much more effective, would be much more of a polluter pay principle rather than a victim pay principle, which we currently have. So can we use this big data to enable science-based policy? One of the challenges as researchers that we face when we are trying to even design policies, leave alone get to the point of implementation, but in the process of designing policies, looking at agricultural, pollution problem, is that even though we have very detailed data when it comes to weather and soil, at a 1 kilometer by 1 kilometer level, but really when it comes to the human decisions that are being made, the agronomic and the crop management decisions, the profits that farmers might be making and the cost to them of various practices, a lot of that is at a very aggregated level. It is just not publicly available in terms of, and so all you can really get is rough estimates at the county or the zip code level from various sources. And so that's been, that kind of really hinders our ability to understand this nexus between food and energy production and its impacts on the environment in a much more precise way, and the cost of regulating or the cost of doing something about it. Also, just improving our understanding of the relationship between crop yields, production practices, and the environment. That is currently, because the data we have is at a much more aggregated level, it's much more harder to really pin that down. So use of this average data that we've had in the past really leads to very inaccurate assessments of the site-specific implications of production on the environment. And big data can be used to design more effective agricultural policies, and to and to understand exactly where we should be targeting it. Okay, but there are a number of challenges before we can do that. The biggest one of that is there's a lot of concern about data privacy, and this question about who owns this data. Is this owned by the companies that is generating this and gathering this data? Does this belong to the farmer? And of course, in all of this, the big concern even farmers have is that they don't want this to be made available to the government for exactly the reasons that I've just noted, that it could be used against them in order to regulate their actions. And so the question is, should this be mandatory now that we have the technology to obtain this data, or should it be left to the voluntary decision of farmers whether or not they provide this data? Of course, it's voluntary, then becomes very difficult to design much with it. And so it raises questions about, how do we maintain data confidentiality and address these privacy concerns? How do we build partnerships where, between private companies, government, researchers, and farmers, so that this data is, is being protected, but it's also available not only for improving private decision making, but also to improve social and societal decision making, and improve the agricultural policies that we can have. I want to turn very briefly to one other example that we've been working on, which is to look at cellulosic biofuels as a way to meet the energy needs while also meeting demands for food. And so the advantage of using this new and emerging approach, which is, the technology is finally here. We currently have 3 cellulosic-based refineries that started production in 2014 in the U.S., although they're using crop residues, and we're talking here a little bit about these energy crops. These are perennial crops, examples being miscanthus and switchgrass, that have the advantage that they are high yielding. They can give you twice as many gallons per acre of land, so you have to divert much less land from food production than you would have to do for corn from corn ethanol in order to meet the same needs for energy. They have a significant potential to sequester carbon in the soil, so as a result of which they have a negative carbon intensity. So per gallon, the carbon intensity of miscanthus-based or switchgrass-based ethanol is negative, which means it's a sink for carbon, as opposed to corn, which is not. And also they can reduce soil erosion because of their root system, reduce nitrogen runoff and leaching instead of contributing to it. So we, this is some work that we've done with Shiming Kai and Siva, and looking at this particular watershed. And so this is a watershed in central Illinois, and we looked at, we mapped it, and we looked at what would be the benefits of changing land use and meeting the needs for biofuels using some mix of corn ethanol and cellulosic ethanol, and what would be the cost of doing that. So I just want to give you a little flavor of the results. And so these maps here sort of show that, it's hard to read, but basically they show the variability in the greenhouse gas intensity of biofuels produced in parts of this. In the case of the first one on the left shows that it's the carbon intensity of miscanthus-based ethanol is negative. Of course, it varies within this watershed, but it's negative everywhere, as opposed to the second map, which is corn ethanol, which is positive and significantly higher. The third map shows the nitrogen yield that would emerge, or the nitrogen runoff that would occur, nitrate runoff with miscanthus, which is very, very small, 0.3 to sort of 1 kilogram per hectare, as opposed to with corn, where it is anything from 2 to 8 or 9. So it's an order of magnitude difference in terms of the runoff that you could get, but also the variability within this little watershed in terms of the benefits that you could get, and therefore it tells you where you might want to in fact plant your to convert land from corn to something else. Would clearly be areas where you have a lot of bleaching currently happening with corn. Okay, so so we did this analysis and we said, all right, supposing our goal was to reduce, not just to produce biofuels, but in addition to producing biofuels, we also wanted to reduce nitrate runoff. And so the second, graph over here shows that as we, from zero of share of cellulosic ethanol, if we increase the amount of cellulosic ethanol, we would get more of a nitrate reduction. But as you can see from here, even if you increase your share of cellulosic ethanol, keeping the total amount of ethanol produced in this watershed the same, you just shift away from corn to cellulosic, the amount of nitrate reduction you'd achieve that way is fairly modest. To get to 9 or 10%, you'd have to have almost half of the ethanol being produced here be from cellulosic sources. But you could get a lot more greenhouse gas reduction because as I said, it is a negative. It's much more effective at reducing greenhouse gas emissions than it would be at reducing nitrates. So you could get a large amount of greenhouse gas reduction by doing that. And so as we think about, well, how should we should we be targeting greenhouse gas reductions with these types of biofuels, or should we target nitrates? You have to really think about how to design policy in order to do that. Now, of course, these are much more costly to produce than corn ethanol, and therefore mean lower profits. And so you need some kind of policy, because otherwise, left to themselves, refineries would produce the cheapest type of ethanol, which would be corn ethanol, and you wouldn't get these benefits. And so there it comes down to, how do we change that mix towards, you can mandate it, but you can also try to use some other environmental performance policies, like a nitrate policy or a carbon tax. And while recognizing that whichever policy you choose, you're going to get some co-benefits in the form of the other, environmental improvement as well. And so this just shows that you could get the same level of nitrate reduction. We looked at 3 different ways. You could get an 8% reduction in nitrates using either a nitrate tax or a carbon tax, or a combination of a nitrate and a carbon tax. And these 3 policies would have very different implications for how much land would be converted from corn to miscanthus. The most effective way to reduce nitrates would be a nitrate tax, and you'd need the smallest amount of reduction, the darker areas being the conversion from corn to miscanthus. A greenhouse policy to reduce nitrates would be relatively ineffective, much less effective, because you need a much greater conversion of land from corn to miscanthus. So there's variations and some alternative choices that would need to be made in terms of, what is the objective and what is the best approach to get to that. There's also the question of the cost, and so as we try to reduce our nitrates and reduce our greenhouse gas emissions, this shows how the cost of that goes up. And then there's a question of who should really bear the cost, and how do we want to impose that through a nitrate tax, which would be very difficult because it's non-point pollution. It's hard to know exactly where the nitrates are originating from. A carbon tax would be a relatively easier policy to impose, if you wanted to do that. But of course, if nitrates is the goal, it would not be as the best way to do it. So let me sort of just summarize and say that it's important to think of this food, energy, and water really as an interconnected system that is linked by the fact that there are crop management decisions, practices that are being chosen by farmers which affect land use, and all of that is happening within a range of policies that are out there that are having both positive impacts on the environment as well as negative impacts on the environment. There is some sort of light at the end of the tunnel through these emerging technologies that can enable increased productivity of food and fuel production with much less negative impacts on the environment. Of course, in order to move in that direction, we need to have appropriately designed policy incentives that reward environmental performance improvements. How we do that is a key challenge. But in order to be effective, we know that these need to be spatially targeted, and they need to recognize the synergies and trade-offs that exist between these various dimensions of the environmental impacts that are generated through our agricultural activities. So I'm going to stop with that and be happy to answer questions.
Terrific. Thank you, Madhu. We have about 15 minutes for questions, so I'll ask our panel to stay here, and people can come up to the microphones. Hopefully they're on. Otherwise, you can just yell like I do. I think it's on the side.
There we go. Got it. Thank you very much. Madhu, this question is for you. A very nice presentation and very intriguing what you're showing about the value of coupling nitrogen reduction along with greenhouse gas reductions and energy crops. One of the things that struck me is you talked about, of course, a carbon tax as one way to do that. And question is, have you looked at, of course, they have cap and trade going on now in California and a number of incentives there. And it's funny how we've talked a lot about California during this meeting. And it's intriguing that they're doing cap and trade and so forth, and there's talk about reaching out beyond California. Have you thought about the possibility of tying some of this in with that, in the sense that from the cap and trade now they're generating a lot of funds, which as far as I'm aware of, they've not completely determined where that was going to go. It might be an opportunity to pull some of those funds here to Illinois. So.
Yeah, we've done a lot of work looking at the policies that are there, in California that could be applied nationally. So California has actually is really innovative in its transportation and carbon policies. They have a low carbon fuel standard, which we've looked at what would be the implication of that for the U.S. Cap and trade, and we've looked at that. But you sort of, I think, raise a slightly different question, which is that, could you have some kind of market system where California could rely upon the Midwest in order to generate some of the credits and, use that to meet their needs rather than trying to do that within their own state. I think that we haven't sort of particularly looked at that, but certainly that kind of trading would be a much more cost-effective way. We know that from everything else that we've sort of studied, that instead of California thinking that they need to produce their own biofuels within the state to meet their needs, it would be much better if they were to transport them from the Midwest, where they're cheaper to produce, and a more, you can produce things here that without irrigation that you would need to use irrigation for over there. So it's, ultimately, in order to, what we really need is a national policy. And in the case of greenhouse gas emissions, you need a global policy, because any other, regional approaches are going to be much more cost inefficient. How these are designed, every place wants to, the emphasis on local and being self-sufficient is sort of overriding the issues of efficiency. So there's a question of how do you, whether they're willing to do that. But certainly, I think there are lots of opportunities. And similarly, if we look at, I know Jim Shortall's done a lot of work on this potential for trading between point sources and non-point sources in terms of the nitrates reduction. It would be much more effective to have wastewater treatment plants purchase credits from farmers who can reduce pollution at much lower cost, rather than trying to keep on improving their methods and going for more costly technologies to cut down, to improve water quality. So, these market-based mechanisms are definitely the way to go. There's a challenge of, there's a political will to do that, and then, I think once you pass that, the markets develop pretty rapidly fast. It's remarkable how quickly markets will develop once you have the policy there.
I've got a question for Jody. So you talked a lot about Clean Water Act. Thinking more about the water quantity issue rather than water quality, and maybe focusing specifically on things like the High Plains Aquifer or the Central Valley Aquifer in California. I realize that's a huge different can of worms, but do you have any thoughts about legal directions going in those directions?
Yes, I do. And it's not such a difficult transition in that if you just fundamentally remember that water quantity can also be a commerce issue. It's more of a political matter on whether you want to more intrusively, perhaps people would argue, impinge on states' rights to police their own aquifers, especially if they're bounded within a state. That's not necessarily true with big aquifers like the Ogallala. So, yes, there is the same sort of power. Whether it would be exercised or not, I think, is a political matter, but it is very clear that in the end, if we come to a quantity crisis and the federal government exerts its leadership, it would be the most difficult for those types of watersheds that are intrastate, and that sort of begs the question of the wetlands, Rapanos line of cases and how far our current use Supreme Court would let the federal government go. But one could also argue that even those intrastate groundwater issues, those produce crops that are traded in commerce. Some of that water may be transported in commerce. Pre-Justice Roberts Supreme Court, I would have said that that would be a pretty easy argument to make, but now that we have Justice Roberts, Justice Alito, Scalia and Thomas, we don't know where Kennedy would fall because Kennedy likes to avoid constitutional issues. It's a paper ripe, I think, for the writing that the question of whether the government would exercise it politically, but also if it ultimately came to litigation, how it would be decided. If I was a betting person, I would say that you could federalize it. But I haven't explored that in a paper yet. I hope that addresses a question.
Thank you all for your energizing presentations this morning. I don't know if it was your presentations or the extra shot of espresso I had that got my heart beating faster, but thank you. My question kind of builds on Siva's discussion last night with Mr. Famigliati and this morning within your presentation, but it kind of addresses all of you. So your mention of the impending water crisis has to do with the food crisis, basically, and an agriculture issue proportionally as consumption is concerned. My concern is that more often than not, this crisis in food gets lumped in with non-food items in the agriculture production. And I was curious if this was something that you witness when it comes to policy implications, if that oftentimes agriculture non-food items are more heavily subsidized than potential food items, or I guess in a new governance approach, Jody, if another possible approach to the water crisis would be redistribution of the food supply, perhaps we could incentivize a more local food supply across the United States and the disaggregation of food supply in California. So do you notice, being the professionals, do you share this concern that non-food items and food items are often aggregated, and in an effective policy approach, do we need to disaggregate these two? Thank you.
Yeah, I think you may have a point. I think we do tend to aggregate all kinds of crops together and not differentiate this. I mean, I have a personal example in China, in the Western China, that I'm actually working on. In the 80s and 90s, 100% of the water was going to food grain production. But with the change of government, with the opening up of the government, in China, the food grain production plummeted, and in place of it, actually, there was cash crops like cotton and chili, and chili for lipstick, not for food. And these kinds of things took over, and there was incentives for that because the rest of China wanted to buy. So, and then in our studies, we also lumped the whole thing together because they all consume water. So we kind of separated, we didn't separate the thing. So maybe there's some value in separating these, because that way you can separate the food security problem from the water security problem.
Thank you. So Dr. Endres provides a very nice framework about how to get things done. And then Madhu talks about market and the economic incentives. Siva talks about optimization. I think that's related to both science and engineering. I'm just wondering how could these three things combine together, integrated for future research? I'd like to hear the response from three of you. Thank you.
So I think actually the three talks, there's some common themes that can be pulled out from that I think are all very relevant to I think what I got from Siva's talk that I think is relevant for applies to some of the stuff that I'm talking about is the importance of culture, values, and it's not, we're not totally rational human beings as a lot of economists like to portray. So there's a need to understand how cultural and behavioral factors will affect decision making and to incorporate that. So it's not enough to have these sort of technological solutions and say, well, this can be done, but ultimately it's the humans that have to adopt it. So bringing that factor into it and understanding how it'll drive behavior and what's going to drive it. And then, while I talk of sort of policies that are that would create the incentives to shape those kind of behavioral decisions, ultimately you need to have actual laws in place. And I think what Jody's talk was nicely sort of portraying was, where should those laws be, and should they be at a state level, at a federal level, and and how do you kind of counter the pushback that you get from the regulated entities who are trying to find loopholes in that. So it's, the policies need to be transformed into laws and regulations in order to be implemented. In order to really complete this whole, you need this combination of the humans, the understanding incentives, and then wrapping sort of the regulatory structure around that. So that's my perspective, but Jody might have other thoughts.
No, I would just add to that we can't forget that in law and policy, it's not just coercion. I wasn't able to sort of focus on the other parts in my presentation, but it is funding for research at universities or in private entities. And it's that ability at a systems level, finding an actor that can tie all of that in and then ask the optimization question, bringing in the values question, and ultimately for me, and I teach this, and I don't know if it's exactly right or not, but you could approach it from values come into play to be decided ultimately in a democracy when we vote. And that's one way in which I think we can corral the sort of behavioral side of things, but that, like we hear, democracy depends on a well-informed electorate. I think I might even pull into my paper, funding for PBS. It might sound tangential, but in order to be able to capture all of the elements that you mentioned so skillfully, I think you have to include a role at a higher level to be able to recognize all of those elements and disciplines. And maybe that's at the federal level, a public level.
You don't have a lot of time, but I'll just say, summarize. I think it's a good question. I call it an optimization problem because that's my background. I'm an engineer, hydrologist. That's the way to frame it. But obviously, what I was aiming for is that, just like Madhu said, economists, hydrologists, engineers, we tend to think the world is rational. We can do this mathematically. But there's a real problem with people's behavior that goes back to their values and their preferences, which is always variable and changing. And in order to really bring that into this so-called optimization problem, even if it is not mathematical, we need to understand human behavior. That means that we need to bring the social scientists into this mix. And that was my goal. That was the goal of my presentation. We need to have the human social scientists into this mix. And then that immediately brings up a lot of problems because we don't speak the same language. I'm sure if there is a social scientist here, they will object to even using optimization to characterize human behavior. So that opens up a lot of problems, a lot of questions, but we need to go through these questions, that we need to bring the natural and the social scientists together, not just economists, but even lawyers and see that we can come to some agree on common language, common ways of doing things, and common ways of doing research. I mean, so that is what I was aiming for. So this is not an easy thing. That's why I call it a rocket science. It is very, very difficult, but we need to tackle that now.
Okay, thank you. We'll stop it there. We have about